Atoms, the building blocks of matter. We're going to look at the history of the atom and how, through indirect evidence, when we've never been able to see an atom, we've still come up with a model and um, where it all began and where we are now. First time you heard about atoms was back in the time about 400 BC. We're looking at where um, we have Aristotle and the Greek philosophers are really big, when everything was thought to be just, you know, air, fire, water, and earth, that those were the only elements. Democritus came up and said, no, that matter was actually these small, indivisible particles that were just stacked together. Um, and Aristotle shot that down because he asked him questions like, well, why don't we just fall down like a bag of marbles then? And what holds us together? And Democritus could not answer those. And so his thought of the atom, which he called atomus, which we now call the atom, uh, went to the wayside for over 1,000 years. As history goes on, we start seeing some things that start building up the atomic theory. We have the law of conservation of mass, saying that mass can neither be created nor destroyed, it can only be rearranged. Then we had the law of definite proportions, saying that elements come together in fixed ratios to make compounds. And then we also have the law of multiple proportions, which says that two of the same elements can make multiple compounds. So, like carbon and oxygen can make carbon monoxide, and they can also make carbon dioxide. Same elements, two different ratios, and they're completely two different things. Carbon monoxide kills you, carbon dioxide, you exhale every time you breathe. Now we've got to Dalton, and Dalton is in the 1800s. Um, Dalton still says what Democritus said back in 400 BC, that atoms are indivisible, small solid particles. That atoms of the same element are identical, atoms of different elements appear different, and that um, they can be, they cannot be created or destroyed, and you cannot divide them, then uh, all we can do is rearrange them. So you can kind of see that the foundations of the atomic theory, the law of conservation of mass, definite proportions and multiple proportions, and what Democritus said about atoms being, just indivisible particles, all of that um, Dalton just kind of puts together and comes up with the atomic theory. Now, according to these, today we do know a couple different things. That we know that atoms are made up of smaller pieces, and that there are isotopes, or atoms of the same element, that can have different masses, but they react the same way. So our atom, this is the smallest piece of an element that still has all the properties of the element. Once you go smaller than the atom, then you go to subatomic particles, and they no longer hold the properties that the element did. The first particle discovered was the electron, and this was by J.J. Thomson. He used the cathode ray tube, uh, working with electricity, and whenever he took a magnet, he would notice that, or a charged plate, that the beam going through the cathode ray tube would always bend towards the positive plate. Well, Ben Franklin had introduced us to charged particles, so we then knew about things being positive and negative charges, and um, they were using new words for them at that time, as far as like charges will repel and opposite charges will attract. Um, so J.J. Thomson concluded that since the beam was being pulled to the positive plate, it must have a negative charge. And this was followed up by um, another man, Robert Millikan, who confirmed that there were negatively charged particles in that beam, and he came up with the mass and the charge, the exact charge of the electron. What he did was an oil drop experiment. He had an he had oil that he would put into a container where they had charged plates, and it would fluctuate the strength of those till it could get it to float in the middle, and then he could determine the mass of it based on the strength of the currents and everything. So they knew that atoms were neutral, that they weren't charged, just because we knew that everything didn't, attract to each other and repel each other, that there was this neutral substance. And so they began looking and found, using the cathode ray tube again, um, Goldstein did this and came up with what we now know as the proton. The nucleus of the atom was the next part that was discovered, and this was with Ernest Rutherford. Ernest Rutherford was actually trying to show that J.J. Thomson's model of the atom, this plum pudding model that they called it, where it was a solid positive mass with negative particles spread throughout. So the positive and negatives were just all spread out evenly. He was trying to prove this correctly. And he took thin gold foil and he was shooting alpha particles, large positively charged particles, at the gold foil. And the majority of them passed through. Well, that didn't coincide with the atom being solid pudding-like matter. Um, so he discovered that basically the atom was just empty space. But then there was a few alpha particles that would ricochet off in very sharp angles, and some even coming straight back. So he also knew there had to be something that was then positively charged that was repelling those, so when it got close enough to it, they couldn't pass through the atom. They were being deflected in different directions. So Ernest Rutherford then came up with what was called the nuclear model. He said the positive and negative charges are not spread out evenly throughout it. All of the positive charges are in the very center, all compact there, and then everything's basically empty space, and way far out then we have the electrons out there. Um, the nucleus takes or accounts for like 99% of the mass of the atom, but a very, very small portion of the space. If you look at the ratio of the nucleus to the volume of the atom, you're looking at taking a small green pea and putting it on the pitcher's mound and then drawing a ring around the outside of Busch Stadium. And that would be the volume of the atom, and that green pea would be the size of the nucleus. Our nucleus, Rutherford said this is where all the protons are. Well, with what Ben Franklin had said about like charges repel each other, then everybody was on the hunt for why isn't this thing just blow up? What's going on? And that's where the neutron came into play. And the neutron is like the glue for the nucleus. They're in between those protons so that they will not repel each other. So that gave us our subatomic particles. Had the electron. We show our symbol as a lowercase e with a little with its charge, negative. And we know these are on the outside of the nucleus. We have the proton, which is inside the nucleus, and it has a positive charge. And then the neutron, which is also in the nucleus, but it does not have a charge. It is a neutral substance. So you can see the symbols are a lowercase letter of the first letter in the name of the particle, and then with as a superscript up to the right, you put what their charge is. If you look at the periodic table, you can see that the periodic table is put in order by atomic number. Well, the atomic number is the number of protons. Now, when we're talking about atoms, you need to know that they are neutral. So for them to be neutral, that means the number of protons that identifies the atom, there must be the same number of negative electrons for it to balance out to be neutral. To find the mass that's in the nucleus, we call this the mass number, and you're going to just simply count the number of protons and neutrons that are in the nucleus. We are going to look at their mass as it being one atomic mass unit, 1 AMU. So, from the periodic table, we can determine what the element is, how many protons it has, how many electrons it has. The mass number is not on the periodic table. That is the atomic mass, and we'll deal with that in just a moment. But the mass number is for one atom. It's talking about one particular isotope for an element. So that is simply just the number of protons and neutrons added together that are located in the nucleus, and that's the majority of its mass. So if I look at this chart, I can determine how many protons, neutrons, electrons, what the mass number is, what the atomic number is, and what the symbol of the element is, all from knowing just a couple of things. If I know the atomic number is 7, I can look at the periodic table. Element number 7 is nitrogen. Um, we know that the atomic number is the number of protons. We're talking about neutral atoms, so that means there must also be 7 electrons. And then the mass number are the protons plus the neutrons, so we have 14. You can practice with these other 3, and we'll look at those in class tomorrow. Isotopes. I've mentioned them a couple times. Isotopes are simply atoms of the same element, but that have different numbers of neutrons, so they have different mass numbers. Hydrogen has 3 common isotopes. Protium, or what's called hydrogen 1, because the mass of protium is 1. There's 1 proton and there are no neutrons, so its mass number is simply 1. Then there's deuterium. It has 1 proton and 1 neutron, so its mass number is 2. And then there's tritium. 1 proton, because it's hydrogen, it's always going to have 1 proton, but then there are 2 neutrons, so it has a mass of 3. the nuclear symbol is going to give you the mass number and the atomic number with the symbol so you can get all the information from what's in that particular isotope in one spot. So I said you use the chemical symbol, and then as a superscript, you write the mass number, and then as a subscript, you write the atomic number. Another way you can write this is if you just write the name and then you put a dash after it and write the mass number. So uranium 235 is just another way of writing it. Since I know it's uranium, I can look on the periodic table and find out its atomic number is 92. So the key part is that it has its mass number with it. The atomic mass unit is what the mass of atoms are recorded in because they have they're so small you can't really talk about them in grams when you're just talking about one particular atom because it's so small. So they came up with the atomic mass unit, and that is exactly 1/12 of the mass of a carbon 12 atom. So since I know that's carbon dash 12, that means that's carbon with a mass of 12. So 12 divided by 12 is 1. So a proton and a neutron then are accounted for one atomic mass unit, and our electrons going to be accounted for nothing because they're so small, we'll just be able to ignore those for our cases. So the proton is approximately 1, so we're just going to count it for 1. And we're going to do the same thing for a neutron. A neutron is actually a little bit heavier than a proton, but not enough to make a difference for general purposes as far as identifying the isotopes. So we just count those as 1. As I said, the electron, we're going to count this as 0 because just to equal 1 AMU, you have to have almost 2,000 electrons. Well, of all of the elements that are discovered right now, we're only up to, you know, elements in the hundreds. So if they're neutral atoms, they're going to have 100 and, you know, 18 protons. So it's also going to have 118 electrons. That's still so far away from being one atomic mass unit that we just ignore it. What you see on the periodic table is called the average atomic mass. This is the weighted average of all the common occurring isotopes in nature for that element, um, so that it's not just an average. Like if I added them all, if I had 5 tests and I added all the scores up and divided by 5, that's an average. But a weighted average, you have to look at that this one shows up more times, so that one's going to affect the mass more in a greater way. Most elements, like the example we looked at with hydrogen, are going to have 2 or more isotopes. And um, we already discussed that the average atomic mass is found on the periodic table. Okay. If we're going to calculate the atomic mass, then what we're going to do is we're going to take the isotopes for this particular element, however many there are. Our formula, I've written it out as if there were just 2 isotopes, isotope A and isotope B. You're going to take how abundant it is, um, how often it shows up in a sample. And then you're going to divide that by 100 just to get it out of percent, so we have a decimal abundance. And then you're going to multiply it by the mass of that isotope. You do the same thing for isotope B, and then you just add them together. And that's going to give you your average atomic mass. So if we look at the example, it says an element has two isotopes. The isotope with a mass of 10.012 AMUs has a relative abundance of 19.91%. The isotope with a mass of 11.009 AMUs has a relative abundance of 80.09%. So to calculate the atomic mass, we're going to take the percent of each isotope divided by 100 to get it in decimal form, and then multiply them by their respective masses, and then just add the two together. So we end up with 10.81 AMUs. And you can look at a periodic table and determine what element this most likely is by finding which element is closest to that. When we talk about the periodic, when we talk about elements and stuff, we cannot pick up one atom of something. So we talk about it in terms of the mole. This is the SI unit for concentration or the amount of the substance. It's abbreviated lowercase MOL. I guess the E was just one, one letter too much. So science people like to abbreviate everything, so we cut it off. So mole of a substance is how much of that substance is present. Well, a man by the name of Avogadro was working with gases and determining that any gas always had the same amount of particles in a given area, which is 22.4 liters when it's at standard temperature and pressure, then no matter what gas it was, the same number of particles were taking up this 22.4 liters. So that's what he called then the mole. And we now call the number of particles in that 22.4 liters of space at STP Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd particles. In books, you may see it as 6.02, 6.023. That part might change a little bit, but it's kind of like pi, how it's really a long number. Same thing with this. There's more than just 6.022. So, um, but Avogadro's number is 6.022 times 10 to the 23 particles. So if I have 6.023 times 10 to the 23rd atoms of hydrogen, then I have 1 mole of hydrogen. So a mole is a counting unit, just like a dozen. If I say I have a dozen eggs, I have 12. If I say I have a dozen handkerchiefs, I have 12. So mole works the same way. If I say I have a mole of marshmallows, then I have 6.022 times 10 to the 23rd marshmallows. It's just a counting number. How much of it's there? So then if we look at the molar mass, or the mass of 6.022 times 10 to the 23rd particles, um, when they found out when you took that mole and you massed it, it ended up numerically the same as the atomic mass, but the difference was the units. With atomic mass, we're talking about one atom, and with molar mass, we're talking about 6.022 times 10 to the 23rd atoms. Well, so the units are different, but numerically they're the same. So if I look at carbon, carbon's atomic mass on the periodic table is 12.01 AMU. Well, that means if I have a mole of carbon atoms, 6.022 times 10 to the 23rd atoms of carbon, and I mass them, that comes out to be 12.01 grams. So that is that's how we can look at molar mass, and that's something we can actually go back in the lab and put on the balance and use and start to work with and make compounds and make solutions and doing things where dealing with individual atoms is not a level that we can work work with. So we look at the majority of our things and molar mass.